I'm Frank Bohlen. I'm a professor emeritus in the University of Connecticut Department of Marine Sciences. I'm a physical oceanographer. I chase currents and the sediments that they carry. I also do a little bit of sailing, and in our experience as a sailor, I'm sensitive to sensory overload. You can get too much information and really have a hard time bringing it all together. So what I hope to present here, I'm here to represent the ocean, is to provide you with a few of the higher points as you go along, with some detail in between, as did Ken. This is not an oceanography course. 14 weeks isn't going to be crammed into 45 minutes or 40 minutes. So here we go. Important. We're dealing with a couple system. Ocean atmosphere. The ocean affects the atmosphere. The atmosphere and its motions and movements that you heard about from Ken affects the oceans. So as you look at these features, remember that. Why do we care about a tidal current? It sort of pushes us around, but it also feeds a fair amount of water vapor. Some of those rapids in the rough waters and the rest. And the water vapor, as you heard, is the fuel that fires the atmospheric heat engine. Gives you a lot of wind. So the air-sea exchange of water vapor as we move along through this is very important. I told you earlier that we love the blue marble. The major ocean currents, surface currents now, a variety of warm water, the red guys, and cooler water, the blue guys, and generally in the form of some gyre. One of those equations you looked at this morning was continuity. So I begin to push the water here. It's a relatively incompressible mass, this mass of water. It's going to move over there, and it might get hit by the wall and turn the corner. There's a continuity to the flow, and you see that in these gyres as we go. We're going to be dealing mainly northern hemisphere, and if you were sitting with me talking about Gulf Stream, I would be talking to you about warm water currents pretty much entirely, but you guys from California know that you have some cold water currents out here too that we have to worry about. Coriolis, you heard about that. Very important to remember that we're operating over the surface of a rotating spheroid. And we have to conserve angularity. And you all know about angular momentum, believe it or not, because some of you, most all of us, have watched the Olympics and seen those skaters out there changing their radius of gyration and rate of rotation. Okay? That's all conservation of angular momentum. And we're doing the same thing as we're pushing a parcel of water, parcel of air over the surface of this rotating sphere because we change the distance to the angle of to the axis of rotation. Okay? Fundamentally, it's all pretty simple if you just think to string some of the pieces together as you go along. The Coriolis force, the Coriolis effect, 2 omega, 2 times the rate of rotation of the Earth, times the sine of the latitude. And you all remember, if you from your trigonometry days, the sine of the latitude goes from a 0 to a 1, 0 down by the equator to 90 degrees to 1. Okay? So you've got a rotation that's going to be dependent on latitude here, rotational effect. Pressure force and Coriolis, the 2 forces we really care about, we're neglecting friction. So we're back to what we heard before was geostrophic, earth turned, simply earth turned. And you may find that hard to believe that friction isn't all that important, but from the mathematics standpoint, it's relatively inconsequential, so we can neglect it. And that's the lazy way of doing it. And that's why for so many years, there was so little work done on near-shore circulation in the ocean, because friction was so important and difficult to parameterize. Okay? Primary factors governing circulation, tides, water column density, and winds. That's what makes water move out there. Okay? Tide, important. The tide is a wave, just like the wave on the beach. Get that through your head and store it away, because it will really help you as you go along and you try to guesstimate what the tidal conditions might be like in this body of water you're going into. Okay? It's a wave. Okay? It's a wave that's caused by the gravitational interaction of the Earth, Sun, and the Moon. Very simple. Those are the forces that are causing this perturbation, this wave, the tide. Okay? Here we are in the wave. This is the quantitative wave spectrum. We're going to be dealing with wind waves a little later. But here we are, the tidal wave periods ranging from 12 to 24 hours, typically. Okay? And you generally, back in Sister Sasparilla's physics class, when you got this introduced to you, were introduced tides through the equilibrium tidal theory. Okay? So you have a sun sitting out here, you've got a moon sitting here, and when they're in line, there's a lot of force and a big bulge right here. Okay? So you got your major amplitude in the feature during the new moon, okay, and full moon, okay? When the moon and sun are in line, major gravitational force, right? And when they're in quadrature, you have a lesser amplitude tide, the so-called neap tide. So we have a spring tide here. It's got nothing to do with March 21, okay? And we've got a neap tide here. Okay. Well, the problem with that, of course, is that there is some friction and the Earth's rotating around and dragging the water with it, and we can't keep these bulges neatly aligned under the sun and moon. And you have some Earth features, the solid mass, solid Earth features that interrupt this bulge traveling. The more accurate way to look at it, just to complicate your picture a little bit, is this amphidromic pattern. You can think of it, this is, you'll hear more in a moment about, this is only for the M2. The primary lunar semidiurnal component of the tide, but you can really think of it as somebody up there throwing rocks in the water. And the somebody up there throwing rocks in the water is our gravitational interaction between the Earth, Sun, and the Moon. Okay? And what you get is a series of features. Here's the North Atlantic. My amphidrome is centered more or less North Atlantic, and there's a wave traveling around that disturbance feature. And here's yours, okay, out here, Pacific. Okay? There's a disturbance with a wave traveling around it. Okay? And the wave interacts with the shelf edges. Okay? And that wave, I'll show you in a second, behaves just like the wave on the beach. It's going to shoal some, it's going to slow down some, change period. It may get to a point where it's even breaking some. You can get the extreme in the tidal wave, just as you can on the beach wave. Here you are. Wave is coming in over the edge of the shelf. When the wavelength, of course, with the period of something like 12 hours or so, realizing that wavelength is a function of period, okay, up here. So with a period of 12 to 24 hours, you can believe the wavelength is pretty long. That means the tidal wave is going to be feeling bottom in quite deep water. And it begins to slow and begins to refract, just like the waves on the beach, steepen up, change period a little bit, okay? All of it dependent on the characteristics of the offshore bathymetry and the longshore features of the basin. You'll see in a moment, okay? You're going to see this one again and again. As we get into waves, the higher frequency stuff from winds, it's the same physics, okay? The wave, Thor in his wisdom with the rock in the water, doesn't produce a single harmonic. You know yourself, if you drop a rock in a puddle, you got a whole variety of frequencies of the wave coming out. So here are the harmonics, the principal tidal harmonics. And here I said before, here's your M2. This is the principal lunar tide. Okay, it's got a period about 12.42 hours. Okay, come on. These are diurnal components. So here's your lunar diurnal, the K1. And we can go down here, principal lunar. Here's principal solar, S2. Here is down, where do we go? Okay, you can get on to longer ones in the lunar, the monthly and longer, and you can get out to 19.8 years if you really want to be a purist about the whole thing. Keep on going. So when you drop that rock in the water, you got a variety of wavelengths produced. And the longer waves are going to be feeling bottom sooner than the shorter, okay? The lower frequency guys, longer wavelength, going to feel bottom sooner than the higher frequency guys, shorter wavelength waves. So there may be some differentiation that goes along. Okay? Ideally, this is what you'd see over the course of 2 weeks. Okay? A very nice near sinusoidal feature, okay, that is more or less uniform. Okay? It's changing amplitude as you go from the spring to the neap. Okay? So this is a 2-week period when the moon went from the full to the quadrature. Okay? Newton line into quadrature. Very nice. Trouble is we hardly ever see that. We more likely see something like this. Part of it has got to do with the fact that the Earth's axis of rotation is not perpendicular to the plane of the ecliptic. And so there is some latitudinal effects. So you might get a higher high and a lower low over the course of a day. Not nice, neat sinusoids that go. Some of it's due to the fact that you got more harmonics than a single harmonic, single K or M, okay? It ain't just the moon that's doing it. The sun also gets into it, okay? And even in some areas, you can find that you don't have the semidiurnal tide, you just have a diurnal tide. All of it has to do with the basin characteristics and the bathymetry leading into that basin, just like it would with any normal wave. If we go to some extremes, we can go down to the Gulf of Mexico. There's a foot of tide down there, hardly any tide. The Romans were amazed when they came out of the Mediterranean to find the tides that are fairly large in the Bay of Biscay, okay? Because the Mediterranean tide is non-existent, basically, okay? Basin characteristics. Here we are in Minas Basin, up Nova Scotia, and you'll see some of the major tides in the world, 54 feet or something like that. Makes for a real climb for a newspaper here. You can send the kid out. Okay? Now, a couple of features you want to keep in mind. So here we are near home. And when I look at this, number one, you look at the width of the continental shelf. Okay? And in this region, 10 to 30 miles, something like that, on that order. And we get down by La Jolla, can walk off the edge of the continental shelf from Scripps Dock. Right? It's pretty narrow on the west coast relative to the east coast, number one. Number two, look at all these little lumps and bumps you got in this feature here. The basin characteristics, the topography, the morphology is complicated. You contrast that with my home. I live here, right there. You see my house. We have a continental shelf that's 80 to 100 miles, 120 miles wide. Down along the East Coast U.S., and we have some features that look like your fjordal basins up along the Northwest, but not many. You got to get up to Somme Sound off Mount Desert, you'll see a fjord on the East Coast. What we do have is a long, narrow basin. A long, narrow basin, similar in features to the Gulf of Maine and north, up into the Minas Basin, okay? Those basin features are important as we go through this. Okay, let's take a look at the harmonics real quick. Here's M2, New London, Connecticut now. That's close to home, excuse me, that's close to home. The M2, we got, this is now in meters, this on the order of a meter of a tide, okay? M2, and essentially nothing else. Everything else gets pretty small. When we come down here, this is the lunar diurnal, okay? This is the principal lunar semidiurnal. When we come down here, here you are, Seattle, more or less here, huh? I'm not sure where the gauge is, but some of you may even know. Here's the M2, 3 on that order. Significantly larger tide, all range, and a significantly larger K1 component. So you've got two waves. One semidiurnal, one lunar, one diurnal, and they're coming together. Remember I showed you that picture earlier? Here we are in New London, and here you see over the course of that's 15 days or so, a spring neap cycle and a fairly significant semidiurnal change in tidal range over the course of the half month, but pretty sinusoidal. And then you come out here and whoops, looks a little lumpity bumpity because you got two frequencies interacting. You have two frequencies interacting because you have such a narrow shelf that the low frequency stuff doesn't get attenuated before it makes it land. In our case, we have a wide shelf. The low frequency stuff gets attenuated before it comes in. Okay? So significant difference in all of that. You got some amplification as the wave moves in, Straits of Juan de Fuca. Here comes that wave coming in, goes by Port Townsend, and you got a range of something on the order, let's call it 9 feet here, and you get down in here, this is now in feet, and we get down in Seattle, and you're talking more like 12 feet. So the wave is shoaling a little bit as it's coming into us, okay? Not much difference down the coast. Here we're at Bush, and here we are down off Oregon. Still looking kind of lumpity-bumpity, same basic characteristics, but pretty much uniform coming down. Makes sense, huh? That wave just sort of came running up against the shelf and looks the same from spot to spot as it comes down. These are tidal currents now in the Straits of Juan de Fuca, which says that you don't have a lot of flood going on. Okay? And you don't have much flood in excess of 1 knot on this guy. Okay? And the asymmetry is due in part, principally, due to stream flow effects. You've got some rivers running in here that are giving you the push out, and they've got going. But you can also see the significant daily variation in speed as you come through this. Now, all of that makes some difference in terms of navigation. As you play with these things, come along, you care how it goes lumps and bumps up and down amplitude for grounding, and you care how it goes up and down speed for set and drift navigation. Basin characteristics. Remember, we got this wave coming in on this piece of ground, like watching the waves come up on a beach and wrap around a rock and then start to retreat around a rock, and you can have fairly complicated flow around the rock or around the rocks if we had a number of rocks. You got the same sort of thing going if you look at the basins as we move up past Vancouver Island, and I guess a good one you guys must know about some of these things. Skookumchuck. And what do you call this? Shelt? Shelt. Handsome place. And challenging navigation. And we were on, when we went up to Desolation Sound, we went through a couple of these very carefully in terms of timing, right? Powerboat or sail. And you get an idea. We were looking at a knot or so, half a knot to a knot and a half, when we were down in Seattle and Juan de Fuca. But here, and this was just what I happened to pick off the other day, this is running out to 12 knots, going down through that. And again, this one, it looks to be fairly neat symmetrical as it goes. But you'd be looking at this carefully in terms of timing and when to go through. Don't forget that any tidal things can be changed by storm effects. The storm has 2 effects. The direct wind effect, dragging on the water, piling up water, so it'll change the tidal range, and pressure effect. Lower pressure, larger tidal ranges. Water will come up a bit. Higher pressure, push the water down a little bit. Okay? This happened to be Sandy coming through our station in the Sound, and you can see we're running along something like in feet. We might be, so say here's on the order of 1 meter or so range, and along came Sandy, and we were out to 2.5 meters, 3 meters. It was an interesting system to go through. Storm effects, always take those into account when you're figuring tide. The other thing, remember that the tidal currents associated with most flows are elliptical. They form an ellipse. It's not a neat matter of flood going east and ebb going west. It matters. Down in our neck of the woods, we used to be able to follow the lobster pot migration, float migration. As you come sailing along over the course of the tide, you can have a tide flooding, and as it's going to the ebb, it migrates. Gets slower, but it's migrating. So you can get significant set and drift over the course of the slack water period. The last thing is one of my favorites in the tides, and most people don't really think much about this. We're dealing with, in your mind, most of the time, when we talk about tides and waves, we're dealing with progressive waves. you know, the seagull gets carried forward and gets carried back. The wave marches along. It's the crack of the whip, and it goes marching along. And so there's a neat correspondence between amplitude and speed. Amplitude, the water's coming up, water's going down, and speed, the current that's associated with it. Here's on the flood, here's on the ebb, pick a name. Okay? But in basins like Long Island Sound, in basins like the Bay of Fundy, that wave marches in and hits up against the wall and reflects from the wall. And some portion, if the wave length is correct to the basin dimension, you can get yourself a standing wave. The wave's coming out is meeting the wave going in. And the wave then isn't progressing. The water level is simply going up and down. Simply going up and down. Okay? A little subtlety to avoid embarrassment with your navigator. Okay? Or your mate, however you want to call a senior member of the administration. Okay? Here's a progressive wave, here's a standing wave. We don't need to go through that. But I want to show you this. Here we are at Montauk Point. I showed you Long Island Sound. It's an east-west tending basin for the most part. Long Island has a tippy end on it with a lighthouse. That's Montauk Point, right at the mouth of the basin. Okay? And here you see these are tidal amplitudes. So here we come to the mean tide level. Okay? And the mean tide level is coincident with zero speed. That's often the way we think about a neat progressive wave. It's going along, and when it changes direction, it goes through very slow, and then turns around and comes back out over here. Okay? So we want to go through that rapids. And we assume that it's a progressive wave marching through the rapids. And we time our arrival for the time when the tide is going from flood to ebb, when the amplitude is going to be going up instead of down. Okay? And everything looks good here. And then we go down to Bridgeport, which is 3/4 of the way down Long Island Sound. And here we have the same condition, the mean tide level. Here we are at zero. And when we look here, we've got a knot of ebb currents still going. It's neatly out of phase, the progressive wave and the standing wave. Be careful in your analysis of the condition that you're playing with. Look at the tables and determine whether the current speeds are in phase with the amplitudes. There have been a number of times in this navigator's experience where we have arrived at an entrance that the oceanographer has predicted would be slack water to find that it was running a knot or two against you. Okay? All right? Just warned is warned. Okay? Real quick on the density. This is now water column density is a function of temperature, salinity, and pressure. Temperature, salinity, and pressure. The primary effect is by temperature and salinity. Pressure is a little effect because water has some finite compressibility if you go down deep enough. The distributions of water temperature, salinity result in spatial gradients in water column pressures. I'm back to Ken McKinley's discussion of atmospheric pressure. Same reasons. Differences in air temperature affect differences in air density, affect differences in air pressure, affect flows. Same thing here. Okay? You guys out here, and for us in Long Island Sound, are living in and around estuaries, areas where the river meets the sea. And in general, you'll have fresh water coming out on top. Fresh water tends to be less dense, okay? And saltier water coming in down below. You have two-layer flow in general. You got a whole department at UW that specializes in nothing but this kind of flow. All right? Thermohaline circulation, driven by temperature and salinity differences. It really, as sailors, boaters, it really doesn't mean an awful lot to us because the typical velocities that are associated with it are in the tenths of knots. It matters a lot in the distribution of mass, how your pollutants move around, how the nutrients for some of the foraging critters, the ecosystem effects are dependent on this. But most of the navigationalism, not much. Typically has a seasonal variation associated with stream flow. And common to most of the northern hemisphere, we have stream flows maximum coincident with snow melt. So that's varied if we have snow, kind of a thing. And these will just give you some idea. There's Columbia versus the Fraser. The Connecticut River, the eastern Long Island Sound rivers are typically down in this level. Okay, so you've got a lot of water coming out of the Columbia. Affects salinities. These are salinities in parts per thousand. Typical open ocean salinity is about 34 parts per thousand, 35 parts per thousand, 3.5%. Okay, so you get an idea. You start coming in. You got salty waters up in here, and you get progressively fresher as you get down into the basins. Makes sense. You're running a lot of water, and you aren't doing much in the way of getting it out. We don't really care, again, from a navigational standpoint, much about it. On the shelf, same sort of thing. This is the seasonal variation in temperature. A couple of stations in Washington and a station off the Oregon shelf, on the Oregon shelf. And you can see a seasonal variation in both. Okay? If we showed you Long Island Sound, I could show you the same kind of picture, Connecticut River, during the high flow events. You generally want to stay out of these things because they carry as much debris as they carry suspended sediments. In general, you won't find too much in the way of currents, although there can be an effect. Here's the Columbia again. This is just, the coloration had to do with suspended material load. It's the best one I could find. I said I chased sediment, so it's one of ours. But it also gives you an idea of the effect of the flows on the effect of the river flow and supply stuff on the continental shelf flows. And you get an idea. Here's a 0.5 meter per second. Everybody knows what a knot is, right? Nautical mile per hour, 50 centimeters a second, 1 knot. Okay, so that's on the order of a knot, half a hundred. Okay, so you got on the order of a knot, and you got some variations in the direction of flow associated with the river flow. Makes sense, but it's all relatively minor, a knot or so of current. Wind, very important, and we could spend all day talking about wind. You've been hearing all morning long about wind so far. Directly drives circulation. Wind blowing over the water pushes the water along. The rule of thumb, remembering the definition of the rule of thumb, about 3% coupling the wind speed to water speed. 30 knots of wind, call me a liar, a knot of current speed, 9/10. Okay, on that order. So if you worry about an added knot, and you might when you're playing with some features like the Gulf Stream, you can get another knot if you give me 30 knots of wind blowing right on the right direction. Okay? Generate surface waves, you all know that. Real quick, the wind stress, here's our gyres. These are average, again, like Ken was showing you earlier. North Pacific, North Atlantic. Here's the North Pacific gyre, and associated with it the major currents. You have the Kuroshio sitting over here, the Japan current, North Pacific drift that leads into bifurcation, okay, with the Alaska current and the California current, and then there's an equatorial return. Surface currents. Subsurface is almost as complicated. In the North Atlantic, same kind of thing. Both of these features, this guy and this guy, the thing that ought to strike you is the strong asymmetry east-west. Okay? East-west. We had the Kuroshio in the Pacific. You had the Gulf Stream in the Atlantic. And you have California, and you have the Canary Atlantic. There's a strong difference, significant difference between what's going on the west side and the east side. It's a long story. It's a little bit of hand-waving to do anything other than to say that it has to do with the need to conserve this rotational momentum. It's got to do with the fact that you're pushing water north in one case and water south in another case. And in order to conserve angular momentum, you've got to speed up the flows on the western side of the basin. That is a very succinct statement of a book that was written by Henry Stommel. Okay? But it's a very interesting feature. You take a look at it. And you'll see it in more or less in the inverse when you take a look at the southern hemisphere. Okay? Here's the Gulf Stream region. I like to take a look at perpetual ocean. That's a NASA clip that's recommended for your viewing. You can turn it on and let it run, and you can watch currents, major currents around the world. It's a run of a model. You get an idea out through the Straits of Florida, up off Hatteras, begins to break up and get kind of meander as it gets across, and then it'll bifurcate into the Norwegian flow and the Canaries current. Okay, Kuroshio, same sort of deal, Japan. Okay, both of them very, very sharp thermal features, Gulf Stream and Kuroshio. Major way to look at it, best way to look at it for most of it is looking at temperature. Both of them fairly narrow, well-defined currents. Okay, you look here, that's 120 nautical miles. And if I brought you a Gulf Stream feature like this guy, I might bring you more like 60 miles. The Kuroshio, a little wider, a little weaker. Gulf Stream, a little narrower, a little stronger. Currents in the Gulf Stream up to about 5 knots. Gulf Stream current. You could add a little bit for wind, remember, to it, but it's on the order of 5 knots. The other thing to know about ocean currents, and we were saying this last night, filamentous. It ain't a single flash of water. It's a bunch of flashes of water. So as you go along playing with this, as a navigator, sometimes you play hell to find these 5 knots of current because you've got to get 30, 40 miles one way or the other. And most of our 5-knot, 38-foot boats take a while to get 4 or 5 miles this way or 20 miles that way. So sometimes the rule of thumb is be satisfied with 3 knots. Don't worry about the 5. Okay? Okay, California. Now, if you look real carefully, and I stared at this a couple of nights, so you got a disadvantage. You get an idea that when we get off the shelf, here's the shelf, sort of hard blue, and things are getting a little more meandery as you get down off the shelf. But mind you, it's a model. It's a little bit of an artist's representation of what things are. The main thing about the California shelf is the sensitivity of the vertical circulation to the wind field. In the case of a stormy condition, that is, the low is affecting you more than the high that you were seeing on Ken's picture, okay? When the wind blows over the water, the wind's dragging the water that way now, I'm water now. Coriolis is pushing it to the right, pulling stuff in here, gets up to the edge of the shelf, there's California, goes down. There's a downwelling flow along here. Downwelling coming down in here. You see this downwelling water, warmer, less saline, nutrient coming down. Okay? The surface water coming down. Under more normal circumstances, what prevails a lot of the time around here is a northerly flow of air. Okay? The northerly going down pushes water offshore. You drag water offshore, it's going to facilitate upwelling along the shelf, along the inner edge, along the beach on the shelf. Okay? That's characteristic here. Very good. Upwelling of cooler water, generally more nutrient-rich water, generally more productive waters. So the fishermen love to see upwelling. And all the way down along the coast, we get into Peru, you worry about what El Nino does down there. It's got to do with the upwelling, downwelling cycles. This is just a picture in July, give you an idea. Here's the wind coming down, and you can see the water's a little bit cooler along the inshore edge here, okay? Because you're upwelling the water, upwelling. This is a clutter, and I'll do it real quick. You can go out and look up the paper. I can give you a reference on this, but it gives you an idea that the currents on the system. Now, mind you, the currents mean in the area are on the order of a knot or so. Again, you're not seeing 5 knots Gulf Stream current running along the California shelf, but you see a variety of features. In the winter, I don't think I have this. Yeah, in the winter, sorry about the blur, I just picked it off this thing. But in the winter, you've got flow going to the south down here, but you've got a countercurrent running up along the inshore edge. This is all of interest to the oceanographers because heat, mass, and momentum matter when we start looking at all this. It's not so much of a difference when it comes to navigation. Okay, so you got the California current, you got a Davidson current, you'll see in a moment. You got a Southern California countercurrent, that's what's showing in here. Come up here, and then you got all these eddies ringing down in here. Okay, here we are in the spring. In the spring, the features, we tend to get a very well-defined coastal jet, close inshore, right down the coast, running on the order of a knot or so. In the summer, things are a little more diffuse, but you have the Southern California eddies down here, a lot of rings coming back in here, okay? Southern California eddy down in here, okay? And here is the fall, and you get the Davison current, so-called, coming back up in here. Here's the Davison current here, okay? Complicated flow regime depending on the wind field. That's what's driving all this up here. Average surface currents you can see running out to something like 1/10 of a meter, 10 centimeters a second surface currents. So you've got about on the order of maximum of a knot. Some anomalous, the blob, we won't even go into it. First seen in 2013, all of the reasons not particularly clear. Potential effects on your weather, you bet. Why? Warm water tends to feed more moisture aloft. More moisture aloft tends to feed all of the system that Ken was talking about. So you care about blobs of warm water from local weather conditions. Okay? The other anomalous condition, of course, is El Nino, and what it means in terms of jet stream locations. Okay? In the winter, you might get wetter here, something like that, and now you're going to get sort of, you love El Nino because it looks to be like you get beautiful weather there. It's a long story in El Nino, La Nina. You need to take a look at it. The cycles are running 2 to 7 years or so, something on that order, and they hang around for a little bit, and you know about it. We don't have time to go into that one. Wind waves, real quick. Important. Can ruin your day, sort of thing. Important. Can make your day. You're a surfer. You really care about the waves. Okay? Size and height of the waves depend on wind speed and direction. They're wind waves. Okay? Duration, how long the wind blows, and the fetch, or the overwater distance in which the wind is acting. If you took a look at my basin, Long Island Sound, we've got 120 miles east-west up and down the basin, and we've got 20 miles north-south. So we got a northerly wind, we got a southerly wind, we got a very different wave condition in that basin than if we have an easterly or westerly wind. Okay? This will be on the exam. Important. Wind blows over the water does not produce a single frequency wave. Just like Thor and his rocks in the tides, it's a spectrum. You get longer and shorter waves. Why do you care? The Farallones. You know the Farallones accident, event? Okay? Bunch of guys sailing along, and of course no marks, and they're going to squeeze, every racer knows they're going to squeeze it as much as they can, and they're going along and they find themselves all of a sudden inside the breaker zone. Okay? Now it's happened to professionals. We were on a tug in South Africa where it happened. Okay? And down in South Africa you got big waves coming up from the Southern Ocean. And the problem is you're going along and you've got a whole flock of high frequency waves. High frequency, short wavelength. Shorter wavelength means they feel bottom, shoal, break further in. So I'm sailing along merrily, dunk, 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 I think I'm outside the breaker zone, and along comes a long wave. Feels bottom sooner, shoals, and breaks offshore of me. All part of the fact that you're dealing not with a single frequency wave, your wave field, you're dealing with a whole flock of waves in that field. Be careful. Remember that. Watch it. You see the swell. You know, things are banging you around, and meanwhile you're sort of doing this. There's some low frequency guys hiding out in all this. Okay? Here we are in the winds. Typical periods are running from something like 5 minutes, the great long guys, but we typically see along a beach something between seconds to 10 seconds, 12 seconds. Typical open ocean wave frequency period, around 14 seconds, something like that. Okay. Here we are inside the fetch area where the wind is really acting on you, Okay. And here we are outside the fetch area. Things are a little more orderly. What's going on? Well, when you start off, if the waves are not long enough to feel bottom, what governs their speed is their wavelength. Here's the speed of the wave, okay? It's proportional to the square root of gravity times the wavelength over 2 pi, okay? So the longer waves are going to outrun the shorter waves in deep water. So I got a storm over here. It was actually one of the ways we used to figure out where storms were. we take a look at the wave frequency over here. We've got a storm over here dropping all sorts of rocks in the water, producing lots of frequencies, okay? And out over in here, we start seeing the low frequency guys coming in. Because they're longer, they've outrun the high frequency guys. No friction now, deep water. Okay? So when you get away from the disturbance, you get low frequency stuff. You get down the Caribbean, you take a look at the sea, you can tell what's going on in the North Atlantic. Because you see the low frequency stuff coming in. Okay? Very useful little thing to keep an eye on. And here's the why of it again, going back. And when we get into shallow water, the wave feels bottom at a point where the water depth is approximately equal to 1/2 the wavelength. Okay? And when you get into shallow water, the speed of advance is simply proportional to water depth. G times the water depth, square root of G times the water depth. Okay? So that the different speed of advance when we start getting in there. And that's what governs the refraction or bending of the wave fronts as they come to the beach. You see them getting all nice and parallel. And then they're steepening up here, and I'm loving to ride right down the front of that guy. Okay? Here's a good source of information. People were asking before, where do you get these things? You know, you get them online, which means you got to receive them. You do have to receive them. That means you do have to have a radio or a sat phone or something when you get away from Seattle Yacht Club and the link we got here. Okay? So here's a system a couple of days ago, and this is the surface analysis by Mr. Acorn. Okay? And an interesting surface analysis. Here we are over in here, sitting over in here. And here's the wave field. Caveat. What is it? Real men don't read labels. Goes something like that. My partner's been saying things like that to me for years about asking directions and reading the labels. Be careful in these guys. Because you see, he talks in meters here. And you will find some, I may have one in a minute, that are in feet. I don't know why they do that. It's just the perverse nature. You'll get a chance to go at Joe in a minute. And all the information is presented in terms of significant wave height. This guy here is, okay, and it tells it in the little box in here, significant wave height, which is the average of the 1/3 highest waves. The average of the 1/3 highest waves. It's not the maximum wave height. This is my station, Central Long Island Sound, and we're looking at a series. This was Storm Sandy again. A 1 meter wave in Long Island Sound is a big wave. Okay? So here you are at Central Long Island Sound, and this is max right in here, and this is sitting down in here. Significant wave height. Significant wave height is 4 meters, and the max is like 6.5. Okay? So the rule of thumb in most safety at sea situations is double the significant wave height for planning purposes. Just, okay, call me a liar, I didn't quite twice, but for safety reasons and the planning, double it. Okay? Other places we can get information. The National Data Buoy Center sometimes has buoys in your location. This one was not too far away. Gives you a nice way to verify some of the predictions you're getting on that plot from Ocean Prediction Center. We have 2 or 3 stations, and I have my own in Central Long Island Sound, that are useful in the New England area for doing this. We've been getting thin on that. You might want to write to your congressman about the maintenance of some of the buoys that are out there. Last point on this stuff, remember that the waves can steepen both because of shoaling and because it can run against the current. So what we have here is from Bill Van Doren's book, is an estimate of just what wind against the current might mean to you. And we picked, there's 2 regions here divided by this dotted line right here. On this side were winds against the current. On this side were winds with the current. And I picked off 10-second waves, and I took 5 knots because I'm a Gulf Stream type. Okay, so half. Okay, and you take a look at that. Bring it over here. If the wind is against the current, if the wind is blowing against Gulf Stream currents, okay, these are 2 curves. One is wave length, okay, and this is wave height. So wave length and the amplitude, the wave height. And what you see here, wind against the current is 0.5 more or less. The wave height in this situation might be from 2 to 5 times greater than the situation without wind against the current. So the height can be significantly greater. Double it. Okay? Call me a liar. Double it. She likes 3 times. Okay, 2 or 3 times. Height. But then the other thing, the damning thing on this, is wavelength might be half. So when you get out to the Gulf Stream and you're sailing through square waves, you are. The whole thing has gotten itself shrunk up a little bit and got a lot steeper. And when you have that, you've got much more possibility of this happening. And this is, we try to stay away from this, okay? Breakers. We don't like breakers. They're the ones that really cause us trouble. Deep water wavelength, I told you that, okay? 5.12 t squared. Waves break when height to length ratios are 1 to 7. 42-degree wave angle, about 1 to 7, okay? And we're trying to stay out of that. Most of the major problems, this actually happened, that's another story, but he came back up with his mast. Shoaling causes length to decrease and height to increase, okay? And that one there, all right? Okay? Rogue waves, they do exist. They were treated as being relatively apocryphal for quite a while. You know, sailors BS. You know, sure you got into this and sure you got into that. But there were some observations from ships, big guys, that would suggest they're real. And this is the Draper oil platform in the North Sea in '95. Most of those oil platforms have wave gauges running on them. And this one recorded this wave. You look at significant wave heights running around 5 meters, okay? And you come along at a very discrete feature out to 17 meters. And the mark of the rogue wave is you go into a rat hole before it. It's got quite a trough. And then you look at this wall sitting in front of you. That's how they've been reported. And this guy would say that was a pretty good observation. It works. Now, in the records, they'll say a significant wave height is something like the rogue wave is something like twice the significant wave height. But you can see here it can be quite a bit more than twice. The dynamics of the whole thing, the physics of the whole thing, not well understood. But we've had some very promising results over the last few years. One is more observations. So this was a series of data actually that resulted in this model to take a look at how energy flows from one wave to another. They thought it was all a process of sort of modulation, spreading energy from one wave frequency to another. And actually, more observations, that's the real thing. There's a rogue sitting there. But the most promising one was a set of laboratory experiments last year in England that were able to reproduce a rogue wave in the wave field in the tank. So they got a wave field running in the tank, got a wave generator down here. And how do we get a rogue wave in this whole thing? It turns out if they ran another frequency wave coming across the dominant frequency wave, dominant direction wave, about 120 degrees in difference, they could reproduce the rogue wave condition, which was very promising. You put that together with the fact that if you take a look down the California coast, Scripps has been monitoring waves off the California coast for years. And they have a very long record down south, all the way along the coast, but particularly down south. And the frequency of occurrence of rogue waves is significantly higher in the Southern California bight, when you get down south of Point Conception. And one of the thoughts is that you have a situation where there's a fair number of different swell directional differences influencing the dominant field. That says that if you were looking, or you were worried about the potential for occurrence of rogue waves, you would look at swell direction, which you can get from some of those wave data. That buoy data actually had swell direction on it, along with the dominant wave field direction. And you can make estimates of the probability of rogue wave occurrence. So we're getting closer to being able to provide some predictions of what's going on. Okay, close up. We're dealing with a couple system. Don't forget the ocean's important to the atmosphere and vice versa in many, many ways, water vapor being a primary one. Ocean currents are driven by a combination of factors, that are going to vary depending on, the importance of each are going to vary depending on where you are, okay? Unfortunately, site-specific. That's always, everybody wants the silver bullet general rule. You get the whole thing out. Ocean currents directly affect set and drift, which I learned not everybody understands what set and drift is anymore, but you can Google it, I guess. Okay? Was an old, that's a term. Okay. The extent to which this affects weather forecast accuracy warrants careful consideration is often overlooked. That is the effect of ocean currents on local weather. Sea state conditions are a function of the extent to which ocean currents and local winds interact. You saw what that means in terms of steepness. And the extreme rogue wave formation is site dependent. And we're making some progress on predicting what's going on. Thank you very much.